Hi, so today I want to go over a problem I found in the textbook that I thought does a really good job in tying together all the Laplace transforms, mathematical concepts, and showing that in a more of a realistic, real-world type of situation. So in this example, we have a spring, a damper, another spring, and a mass. And I have that the mass is 0.1 kilograms, so about the weight of an apple. We got a B2 of 0.4, K1 of 6, K2 of 4, and a force, a constant force, of 10 newtons. So in this case, we want to basically find out how this is going to oscillate or pretty much move, is what we're trying to find out in this one. The very first thing we want to do is find out two equations that we can make and find a transfer function for. So what I'm going to do is basically split this here because it's in parallel. We want to get two equations, and the first equation is going to be, let's do sum of the forces of the mass. So this is F equals ma, and in this case we have m, and then I'm going to be referencing it to this x. So x dot dot equals, we have, let's say that that's positive, so we have a pt, and we got negative k1, we'll start with k2, then we have x minus y, and x and y, these are just displacements. We have minus k1, and we have x, and the second equation, we're going to take it right here. So we're going to basically do a free body diagram of what is happening right here. So sum of the forces at, let's say, point y is going to be m y dot dot equals, so we have a we should have a k2 and x minus y. Again, we're saying that that's positive going down, and we have negative b2 and y dot in this case. And we could first say that because this part is a particle point, we're saying that this has no mass, so that becomes 0. And now we have our two equations, and we want our transfer function to look something like a force that's inputted here, and our behavior here. So when we do this, we could kind of do this in this time domain right here, but it'll be easier if we use Laplace transforms and then kind of compute it out, because we want to get it in this form anyways, in the S domain. And what Laplace transform does is basically makes it easier for us to algebraically manipulate it rather than having to derive or do derivatives and integrals of everything, which I guess is possible, but transfer functions make it a whole lot easier, and it will go through more algebra than anything. So the first transfer function, we do Laplace of Fm, that's going to be m, and then we're going to assume that the initial conditions are 0, so we have ms squared x in the S domain equals p in the S domain minus k2 x in the S domain minus y in the S domain, parenthesis close, minus k1 x in the S domain. So that's what we got now. In our second one, actually let me kind of simplify this out first. So then we have xs in the S domain, we have ms squared, and then we got, coming over here, got plus k2 plus k1, that's going to be ps plus k2 in the y S domain. And from this one, we're going to take this one here, take the Laplace of sum of the f at y, and that one is going to be, we're going to take this one over on this side because this is 0, and b2s y of s, and that's because this is a derivative, and the Laplace of a derivative is going to have s, and we're going to say that initial conditions are 0. And let's see, equals k2 x in the s domain minus k2 and y in the s domain again. So now we got these two equations, and we can say, just by looking at this, that y of s is going to be, so we're going to take this one over here, going to be, let's see, k, y, did I even do that right? Then y of s plus, yep, going to be k2 x of s over b2 s plus k2. So we can see that but the y's over here, and then we did ys is in parentheses b2s plus k, and then over that, so that now we have this, and we were going to bring this y of s back into that y of s, and when we do that, we're basically going to have, man, this gets long, sorry, x s m s squared plus k2 plus k1 equals b of s plus k2 and k2 squared now, over, we have b2s plus k2, and then we have our x of s here. Now we want to bring this one over here, right? And then we could do this mumbo jumbo, which is going to be yet another long one. I have xs, but I want to show you guys every step just so we don't get lost together. And we have ms squared plus k2 plus k1, and then because this comes over here, it's going to be a minus, and that's going to be k2 squared b2s plus k2, and that's going to be p of the s domain. And remember, we want to get our transfer function to look something like this right here. So with the two equations that we made, we got two different Laplaces, and then now we have p in the s domain, x in the s domain, and we would just have to bring this over on this side and this over on that side. So it's going to be 1 over all of this guy. And I can, sure, why don't we go over and simplify it even more. So I'm going to delete this here. And show you guys. One over there, simplify. And sure, I'll go through the algebraic expressions. X of s, p of s equals 1 over m s squared plus k2 plus k1 minus k2 squared over b2s plus k2, and we're going to multiply both sides by, so up on top, b2s plus k2, multiply up here, b2s plus k2, and we have our transfer function to be b2s plus k2 over, now we have b2s plus k, multiply that by ms squared plus k1, or k2 plus k1 minus k2 squared, right? And then we can distribute this out, which I will do. So we have b2 ms cubed plus b2s k2 plus b2 sk1 plus k 2 ms squared plus k2 squared, k2 squared plus k2 k1 minus k2 squared. There we go. So kind of getting ugly yet again. And we can notice that the k2 here, and there's another one somewhere right here, they cancel out, and we have a 3 here, we have a s squared, and we have 2 s's right there. Once we simplify, we will have our transfer function, which I will rewrite xs over p of s equals b2s plus k2 over mb2s cubed plus mk2s squared plus k1 plus k2 b2 s plus k1 k2, so just right there. Then we're going to plug in the values here to find that it's going to be 0.4s plus 4 over 0.04s cubed plus 0.4s squared plus 4s plus 24. We're going to multiply the top and bottom by 100 over 4, or 25, right? So we get our transfer function to be 10s plus 100 over s cubed plus 10s squared plus 100s plus 600. Now that is our transfer function. So we went through there, put into 2 different equations, came over here, put it in the Laplace domain, got our transfer function, and after we plugged in the values, it looks very, very nice. So what can we do after we get our transfer function? We know that transfer function is xs over ps, and so if we multiply it by ps in the s domain, we could get x of s, and then once we have x of s, we could do inverse Laplace to get our x back in the time domain, right? So that's what we're going to attempt to do. So once you got the transfer function, delete this here, and let me rewrite. So now that we got our transfer function, we're going to multiply it by 10 newtons over s, because p of t, once we take the Laplace of it, is going to be 10 over s, right? So x of s is going to be 10 newtons over s multiplied by our transfer function that we had earlier of 10s plus 100 over s cubed plus 10s squared plus 100s plus 600. And then let me just, for 100, going on to another slide. And, theoretically, it would be really nice if we could just take the inverse Laplace and then boom, we'll get it. But we can't, unfortunately, because we don't have an expression in the Laplace domain, in the Laplace function, to make this into the time domain straightly from this. So we have to do some more ugly partial fractions so that it will let us use the table on the transfer functions from the Laplace functions to make it into the time domain again. So the easiest way to break something like this down is to actually graph it. And when you graph it, let's say hypothetically you have a graph, and then since it's a cubic, I'm not so sure, let's say you have something like that, or I think this one looks more like more straight or something like that. But so after I graphed it, I found that this only had 1, 0, which means, I don't know, it didn't look like this, but let's say it was right here, and the 0 was actually at negative 7.4204, 0, right? So it was right there. And now that we know one of the zeros, we could find out that this actually distributes out. And we know that so it would have to take the form of s plus 7.4204, and then something is going to be this cubic function. And what I'm going to do now is long division. So this is why I like this problem here, is because it's going to tie in a lot of common mathematical toolboxes that you can use to solve a problem like this. So what I'm going to do, we have s cubed plus 10s squared plus 100s plus 600. And like I said, we have our s plus 7.4204 right there. We want to see what multiplied by some anything up here actually equals this. And sometimes you might be left with remainders and whatnot, but in this case it's going to be much easier, and you're going to see why. So if I do s squared, we're going to have s cubed plus 7.4204 s squared. Subtract that, we're going to have 2.5796 s squared plus 100 s plus 600. Now notice there's going to be some rounding in there. But if we do plus 2.5796 s squared here, then we're going to have the same one here, 96 s squared plus 2 multiplied by that would get me 19.042 s. Then we're going to subtract that again. That would go away, and then this will become 80.9058 s plus 600. And then you put the 80.9056 here, and multiply that. We're going to have our 80.9058 s plus, and that actually becomes 600. Perfect. So in this case, now we know that this multiplied by this is going to give us that, right? So keep that in mind right there. I'm going to erase this just so I have more room. So our x of s now becomes 100 s plus 1000 over s multiplied by s plus the 0, right? So 7.4204. And then what was on the top part? It was s squared plus 2.5796s plus 80.9058. We're getting there. We could almost do the partial fraction, right? Because this becomes a over s plus b of s plus 7.4024 plus, since s squared is the highest, it's a second degree polynomial, we're going to have to do cx plus d over s squared plus 2.5796s plus 80.9058. And so now we, this is much easier to do, and then you're gonna know that that's gonna be another pain in the butt, but we can almost do our inverse Laplaces if it's in this form, right? But we're getting there. We're getting closer and closer. So to do something like this, what we're gonna have to do is basically, I'm gonna write it out. So we have a multiplied by s plus 7.4024, multiply all that by s squared plus 2.5796s plus 80.9058 plus b s squared plus 2.5796s plus 80.9058, and then we have cx plus d, s, and then s plus 7.4024, just like that. That is one heck of a long equation. I understand. But the cool part about this is that we could put this, sure, you're going to have to find all that, but once you have your main equations are going to look like as3 plus 10 s squared plus 100 s plus 600 plus bs cubed plus 2.5796 bs plus 80.9058 bs plus cs cubed plus 7.4204 s squared plus d squared plus d 7.4204 ds. So this is this simplified, and now we can find out that, I'm going to erase the top part, that we can put this in a matrix, and we could use Gauss Jordan Elimination if I'm not mistaken. That's the name of it. We have a 1a s to the cube, and we have 1b s cubed, and we have 1c, and we have 0d, and we've got, let's say, we got 10, we got 2.579, we got 7.4204, and 1, So these are going to be the s squared, bs squared. I think I missed a bs squared. Yep, this one is a squared. And then 7.50 and 1d. Then we have 100 s. We have 80.9058 bs, and we have a 7 point, or we don't have, do we have an s in this one? For b, c does, C does not have an S, so that's a 0, sorry. That's a 0, and then D has a 7.4204 S, and then we have a 600, 0, 0, 0. So this is our S cubed, our S squared, our S's, and our 1's. And that has to be 0, 0, 100, 1000, because we want, what we're trying to do is, like I said before, A of S plus B S plus 7.4024 plus C S plus D equal to, what was that? Here it is. S squared plus 2.5796 S plus 80.9058. And we're trying to find out from these 4 variables what the 4 variables are to make this equal to 100s plus 1000 over that big equation that I'm going to kind of simplify, or kind of round off, should I say. So we want to find A, B, C, and D to make this here, and that's why S is 100, and then the 1's are 1000. And once we put we could do this the long way by making this 1, 1, 1, 1, but I'm going to spare you the time because it's going to take a lot of time, and just tell you that A came out to be 1.666, B is negative 0.29756, C became negative 1.36909, and D became negative 5.739. And you could check if these answers are correct by doing 1.66 minus 0.9675 minus 1.3909 should be 0, and then when you do 100 times that, 80 times that, 0 times that times that should be 100, and then that times 600 should be 1000. And it looks right. So what we found out, that we could get this mumbo jumbo into a simpler form like this, that we could eventually take the Laplace, the inverse Laplace of, to get our x of t in the time domain. So I'll leave you guys there for that one. I'm going to erase the board. Let me check my memory. All right. Okay, so we have our A, B's, and C's. I'm going to rewrite the x of s up here, kind of small, 1.666s plus negative 0.29756 over s plus 7.4204 plus, I'm going to erase that here, plus we have negative 1.36909 s plus or minus 5.739 over s squared plus 2.5796s plus 80.9058. And we're so close, you know, we can make that 1.66 in the in the time domain. We can do that e negative 0.2976 to e to the negative 7.42, but we still can't get this, unfortunately. And what we're gonna have to do here is actually use perfect squares. Because if you take a look at the Laplace table, we know that if we could get this into a form similar to s plus a and s plus a squared plus w squared and or omega s plus a squared plus w omega squared. If we could get it in this form, we can make that into e to the negative at cosine wt and also e to the negative t at sine of omega t. And we are almost done. The way we're going to make this happen is we're going to massage the function. So we want this to look like that. So what are we going to do? We are going to use a method of perfect squares, and so in that case, because we want it to look something like that, we could do s squared, s, and then get half of that, which is going to be 1.2898, and do that same here, 2898, and so you got 1.298s, 1.298s, and then that times that was 1.66356, and we're almost there. We could simplify that to all this to be negative 1.36909s minus 5.739 over, now it becomes s plus 1.2898 squared, and we already used 1.66356 here, so we have to do 80.9058 minus 1.66356 to get 79.2422 here. So you can see that this is almost looking like this. What do we have to do to make this into this? We have to use something that's very similar to partial fractions, but yet again we gotta take this function out to dinner again and massage it to get our final equation. And we could take a look that this looks like omega squared, and this has to be s plus a, where this is s plus a. If we want to do that, what we're going to do here is something very, very cool, in my opinion. We are going to take negative 1.36909 s minus 5.739 over s plus 1.2898 squared plus 79.2422 equals a multiplied, so we want to find a again, there's going to be an a multiplied by, since we want it in this form, notice that that's omega squared, but that one's omega, which means that we want to get square root of that, which is going to be square root of 79.2422 over s plus 1.2898 squared plus 79.2422 and we want to find a b multiplied by s plus, here, let me get that out of the way, get this out of the way, s, so plus 1.2898 over the same one as before. And notice all we're doing is we're forcing it to make it look like this. Because if it looks like this, we could take the inverse Laplace of it, and it looks almost like cheating because we're forcing it to make it turn into that equation. But it's not really cheating because everything we're doing is mathematically okay. And we're not really changing anything. We're finding constants to make it look like that, but still equal the original equation. And that's what's so fascinating about these partial fractions and these kind of techniques right here to massage the equation to make it into what we want and what we're looking for. So let me get this, and this is much more simpler than partial fractions because all we're dealing with now, the square root of that is going to basically make this whole equation turn into, since the denominators are the same, we're going to have bs right there plus, so that's going to be 8.90181a plus, so the plus 1.2898b, and I just wrote it this way so it's easier to kind of see what it needs to become. This is negative 1.369 s minus 5.739. And we could put this in a matrix again of a very simple 0, 1, negative 1.36909. And we got 8.90198, blah, blah, blah. We got 1.289 and negative 5.739 to get our a's and b's to be a equals negative 0.4463 and our b to be negative 1.36909. We're almost there. It is fantastic. We are so close because all we have to do now is put a and b back in here and get our x of s. I'm going to delete all this here. Hope you guys don't need that. And I'm going to leave that there because now I'm going to show you what we all did. What we did was now we changed this whole x of s to be 1.66 s plus 0.29756 s plus 7.4204, and we have our a, right? Our a was, dang it, did I write it? Yep, I wrote it. Okay, good, good. Really glad I wrote that. 4463, and we have our 8.901, and we have our, you know what, I'm just going to leave that as square root of 79.244, just so it's not confusing. I'm not doing anything crazy. Squared plus 79.242. And finally, if I could squeeze this guy in here, negative 1.36, and for s plus, so this is our s plus a, 1.2898, and we have the same, I'm going to kind of round it here just so I can fit it on the board. So this is what we have. This is our x in the s domain. And you can see that we are now at a part where we could take the inverse Laplace to make this a time function. And what we're going to do is going to say that inverse Laplace of x of s is going to be, that's just going to be 1.666. That's going to be negative 0.29756 e to the That's our A, so that's going to be negative 7.4204 t. And we have our negative 0.4463. We have our e to the negative 1.2898 t, and that's going to be sine of our omega, which is 8.89 t, minus, I'm going to put this one down here, 1.36909 e to the negative 1.289 t cosine 8.89 t. That, my friends, is x of t. So this equation represents what would happen if I have a step function of 10 newtons here. So what does that mean? That means that if I put, so because 10 newtons is force times acceleration, which is mass on this acceleration. We know it's 9.81 for gravity, if that's our constant. Mass is roughly 1.02 or something, right? So that means that if we have a 1.02 kilogram thing, now remember that our initial mass was 0.1 kilograms, so we were putting something that's 10 times heavier on here, like a 1 kilogram weight. We're sticking it on here and seeing what would happen. We could say that because to estimate what would happen, how much end displacement it has, we could say that if the K1 and K2, since these are in parallel, if we assume that K is, let's say, the total K and B all together is roughly 5 or something, we know that because force of a spring is Kx, and if we assume that K in this whole entire system is, let's say, 5 Newton over meters, and then we don't know how much it's going to displace, and we say that the force is going to be 10 newtons here, we can assume that it's going to roughly be 10 over 5, which is 2 meters. We're going to assume that this is going to be 2 meters down. If we put our end result is going to look like 2 meters down, but what's going to happen is that as time goes away, this becomes 0, this becomes 0, this becomes 0 when time is closer to, I guess, infinity, you could say. We're going to be left with 1.666. That means that as it puts on, and after it oscillates a little bit, it's going to be displaced at a final value of 1.66 meters. Fascinating, right? We estimated about 2 meters, but through this derivation of calculations, it's going to be 1.666. And you can even put this in MATLAB and figure this out much easier. But I wanted to show you guys a step-by-step way so that we could take that ugly equation, break it down, use inverse Laplace to get our final equation. Hope you guys had fun. Thank you so much for sticking with me. Appreciate it.